With that, we will go to our second presentation from University of Oklahoma, development of user-friendly tools and decision-making algorithms for service life design of ABC bridges. Dr. Shima Mohebbi is going to present this. Dr. Mohebbi.
So thank you all for tuning in and attending this webinar. Our project is about developing user-friendly tools and decision-making algorithms for service life design of ABC bridges with focus on longitudinal deck closure joints. My name is Shima Mohebbi, the PI, and Dr. Royce Floyd is a co-PI, and two graduate students from computer science and civil engineering department have worked on this project. As you know, prefabricated deck elements are connected by cast-in-place closure joints on site, and the performance of closure joints under service loads and extreme events is critical because it affects the structural integrity. The state-of-the-art of closure joint design method for service life and durability are synthesized in a recent publication by ABC UTC. The guide presented about 5 alternatives that could be used for closure joints, and these alternatives include different geometry, shape, and reinforcement configuration. And for each alternative, several mitigation strategies along with the estimated service life and cost items are presented in the guide. The mitigation strategies are the combination of several solutions such as increasing deck and closure joint thickness, using normal strength concrete, UHPC overlay material, or a stainless steel reinforcement and bottom sealers. The guide is comprehensive, but it's not user-friendly for bridge engineers and state DOTs to use the guide and implement it in their design. So the main question is, how can we make it user-friendly, which assists engineers to make final design decision? Spreadsheets are commonly used by state DOTs and industry to assess the service life. Spreadsheets have all the typical limitations, including manual updating and system dependence. So the overarching objective of this project was to design and implement a web-based decision support tool based on the steps presented in the guide. And the tool is visual and allows users to easily navigate through the design options, design steps, geometry, material properties, and modes of failures. Particularly, it calculates the estimated service life of the bridge deck and initial cost. We then utilized a multi-criteria decision-making algorithm for trade-off analysis and to help users choose the best option or mitigation strategy. So to achieve the goal, we have 4 main tasks. The first task is to design the architecture of the decision support tool. The next step is the content flow identification, algorithms, analytics, and dashboard design. And to this end, we first translated the design solution presented in the guide into unified modeling language use case diagrams. The main purpose of UML is to define a standard way to visualize the way a system has been designed. We also designed a series of interactive questions based on the decision-making criteria to walk the user through design solutions. We also solicited feedback from the research advisory panel and several state DOT engineers and updated the decision support tool based on their feedback. The following step was naturally the implementation. Now I'm going to walk you through each task and then present the implemented web-based tool. As you can see here, the architecture has 3 main layers: graphical user interface, application server, and database server. The first layer is the forms and interfaces with design where the specific parameters need to be given by the user to assist in identifying the list of closure joints and mitigation strategies. The application server includes data models and analytics and algorithm to calculate the service life costs and trade-off analysis. We can query information, delete, insert, or update the information when available. Based on user requests, scripts are executed on the web servers to generate output on the user side. Specifically, the web-based platform we used in this project was Python-based open source. Its architecture is based on the model view controller design pattern. It means that the application consists of data models, presentation information, and control information. And based on user input, it can manipulate the data models. So it means that this is flexible and a comprehensive platform, which gives us the opportunity to add different levels of computational intelligence to the application. For instance, in the future, we may want to add some advanced text and data mining algorithms to make the application more dynamic and intelligent. Under task 2, content flow identification, we designed UML use case diagram and a database that we are going to see them in a minute. Also, to better understand the relationship between input parameters and mitigation strategies in the guide, we first designed and tested an Excel-based decision support tool based on the use case diagram, and this tool served as our reference point for developing the web-based tool. Here you can see the system level UML class diagram, and each rectangle represents classes and their attributes. There is a main class in the middle, which initially establishes a database connection using the parameter MySQL DB class. This connection helps in getting access to the database where the user can retrieve the data and ask questions. There are other classes such as closure joint, joint properties, mitigation strategies, cost, and service life analysis, and fault tree representing factors affecting the service life design, such as traffic load, hazard, and operational defects. This is a snapshot of the database we designed for this tool, which supports a spatiotemporal data set. Overall, you can see the number of tables and relationship between classes. In this figure, you are not meant to read tables and their attribute. However, I would like to point out that in designing relational databases, we are also concerned about the inheritance relationship between classes, and so we define aggregation, composition, and generalization relations and normalize them in the database. Here you can see 2 use case diagrams. The user is a primary actor who initiates the system. And the project, the database is a secondary actor, which provides the necessary details to process the request. So the user selects the closure joint types and properties. In the second use case diagram, the user selects the mode of failures or factors affecting the service life, and the decision support tool will process the input and generate the mitigation strategies. Another exciting part, you can see a demo of the web-based tool. This is the first and introductory page explaining the objective and some background information. You see 2 buttons on this page. First time users need to register, and afterwards they can use the login page. For user registration, there are some fields with asterisk, which are mandatory, such as first name, last name, organizations, and city, zip codes are optional, but state, as you can see, is mandatory because some parameters populated by the tool is state-wise. So we use this input to customize the parameters for the user. And then email and password. After finishing this step, the user can go to the first form, joint properties. You can see some information tabs here. We are asking for closure joint width limitation. And the information tab, we are explaining we are providing suggested values, and this parameter will be used for cost calculation. So this then based on this information, the user can input the value for the width. So for deck thickness, inter thickness in inches, and then the user can choose reinforcing bar type, joint direction, and joint depth. Under a local site requirement, we are asking for a structure number, year built, site location, bridge location. So if they are in urban or rural areas, and this is like a drop-down box, and the user can choose from these options. And then we are asking for bridge lengths in feet, bridge width, and the number of lanes that this parameter will be used for calculating the cost. In the next step, the user can choose closure joint types. In the guide, we have 5 alternatives. So these are like a thumbnail option. If they click on it, then they can see the configuration as well. So the user can choose either of this, any of these options. So let's say they choose the normal strength concrete with the straight bars, and then they go to the next step. And here we are asking the user to select factors affecting service life. And then based on this factor, we will generate mitigation strategies based on the fault tree. So I would like to draw your attention to the hyperlink here. So if the user click on this, then they will see the reference for the fault tree analysis, how it is calculated. So let's say under traffic induced, the user choose fatigue and wear abrasion, and then on the second form here, under the natural and man-made hazard, you can see the options, so they can see any of them which apply. And then here, based on those parameters, we generate the suitable mitigation strategy. So that generates, that provides some general recommendation based on the closure joint type and the factors the user chose previously. So you can see, for example, for the traffic-induced fatigue, the suggestion is to use the LRFD specification, or for the traffic-induced wear and abrasion, can implement concrete mix design strategies or membrane and overlays. Now, if this is a new design, so the user can go back and choose another closure joint type, and then choose other factors and see what the mitigation strategy would be. So with this button, they go back to this form, and then they can choose another closure joint and other factors that can affect service life, which applies to the area, and they are site specific. So this form dynamically populate the mitigation strategies based on the information in the guide. So after this, we can move on to the service life calculations. So in this form, we are asking the user to input parameters, and we are using the fixed second law to calculate the service life, and we calculate the time to initiation. And here you can see that we have the information tab, and under the information tab, we are explaining the assumptions we made for calculating the service life. We are assuming only one-dimensional chloride ingress, and also our calculation does not account for cracking in concrete, and which will reduce the service life, and UHPC is not considered for calculation, as assumed to have a service life of more than 150 years. And then epoxy coated bar has similar performance to normal bar, and it is a hyperlink, so they can see the reference that we use for this assumption. And then here for the parameters, we are providing definitions, the units, and also some suggested values. For the first one is the chloride concentration, so we'll provide with range. And we also encourage the user to modify these values based on the site-specific requirements. But if they decide to go with the suggested value, then those will be used for calculating the service life. But the user has the option to input their own values for the closure joint. The other parameter is the diffusion coefficient, the chloride threshold. This one is a statewise parameter. So it means that from the references based on the state, we had different values, and and the suggested value that you see here is, for example, for the state of Florida, because the user chose the state of Florida when they were logging in. So this option is also dynamic based on the state. The other parameter that we need for the calculation is the cover depth. And there is an information tab for this one. So higher cover depths give you higher service life. And then we move on to the cost input. Here we are asking the user to provide the material unit cost. And these are the assumptions for calculating cost in this tool. So we are encouraging bridge engineers to revise and modify these default values to fit the specific project needs. Also, initial cost is calculated based on the material cost, bridge lengths or widths, number of closure joints, and number of bars. And here you can see a hyperlink, which takes the user to the reference where we got our default values.
Dr. Mohebbi, sorry, can you finish in a minute or so?
Yes. So similar to the service life, here you can see the user has the option to use the suggested values or provide their own value. And then the important part here is that we are asking the user to provide a reference or weight for the service life. So here we are using the TOPSIS algorithm as the multi-criteria decision-making process. So it means that if the user wants to give higher priority to service life, they enter higher value, a number between 1 and 100. So here we have for the first scenario, let's say it takes a few seconds to load. So the default values are equal weights to service life and cost. And then after they input the importance, then they will see the best mitigation strategy. So I'm going to fast forward a bit here. Okay. Overall, based on the user input, we generate the best mitigation strategies, and then we ask some additional information about the inspection data, if the user is willing to provide, and that would be the end of the tool. So I guess I'm 2 minutes more than the assigned time. So if you have any question, I'll be more than happy to answer via email.
No problem, Dr. Mohebbi. Thank you very much. I mean, it was worth it to hear what you had to say, and it is really a nice tool. We realize that, and so hopefully we will have you in our next seminars or so to, I know that product is finished, but we'd like you to have more time to explain everything. Thank you again.